Okay. Whoops. Yeah, I didn't want to. So today is what I've called part one, segment one. All of part one that I've set forth is all prerequisite material, so things you should have seen before, but we'll review parts of them. Other things may be that maybe I put a little different perspective on the same thing. So, but we're going to go back and look at just exponents and rules for exponents to make sure we have those down. So you learn exponents as what? Shorthand for if you start listing factors and multiplying. So you start with something like 3 and then 3 times 3, 3 times 3 times 3, and so forth. And so you call it, 2 factors, so I use a 2 as a superscript, right? And then call that the exponent. So things that now, I think actually they start probably, first, second grade even, talking about that maybe. Because it's not too hard to make, once you know how to multiply, not too hard to make sense out of that part of exponents, right? And then you have, if you write 3 to the 4th, this whole quantity technically is called a power, right? So 81 is the 4th power of 3, since that would compute to 81. And then the parts of the power would be the exponent, which is 4, and the base, right? Whoops, almost pointed the wrong place. And so it's made up of a base, which are the factors, and how many factors is the exponent. So, but that's a rather simple setting for exponents. That's where you start. And then you have things that act like that, but maybe not as easy to define. If you start listing, well, that'd be 1, this would be 2, cubed, 4. Whoops. Come on, stylus, catch up here. I'll have to slow down. So the basic way you come up with exponents is you start multiplying by factors, but if you started the other way, like at 3 to the 4th, and then wanted to go the other way, then you would what? Divide by 3. And so that allows you to extend this. If I divide by 3, the next one would be 1, wouldn't it? And divide by 3 again, I would have 1/3 and 1/9 and so forth, right? Oops. So now I have this sequence of 3's where if I multiply by 3 I go up, if I divide by 3 I go down, right? So now we'll just use the same notation so that come on. Oh, get the right one. This is 1, 2, 3, so this better be 0, 1, 2, 3, 4, right? And this one is the number of factors before that, so -1. And this one better be 3 to the -2. So in that way, multiplying by 3 reduces the adds 1 to the exponent. Dividing by 3 subtracts 1 from the exponent. So it just extends the definition of the exponents into 0 and the negative numbers. So in general, if you take anything and take the 0 power, you should get 1. Right? So regardless of the base, except it doesn't make sense if x is 0 because you can't divide back. And the whole thing about powers of 0 doesn't come up too much because once it's always 0. But you can't have negative exponents and such, or 0 exponents. And if I take x and put a negative exponent, that's the same as, well, it was just 1 over, wasn't it, when I backed up? So, same as dividing by that many factors. So negative exponents are equivalent to what? Reciprocals with positive exponents. So 2 basic rules. 0 power always gives 1, negative is 1 over with the positive, and vice versa. Some other rules are if you take so many factors and then multiply by so many more. Well, this says there are 2 factors and 3 factors, so how many altogether? So it's just adding the exponents. So you have that basic rule, whatever the base or the exponent. If you're multiplying those 2 powers with the same base, you just add the exponents. Oops. And division, well, you can do different things, but you can see you're getting rid of factors, so instead of adding, it becomes subtraction. So you start with n factors, you get rid of m of them, right? Or if you prefer, you can change this. Because if you don't like denominators, you could change that to x to the minus m and then just use the other rule. So it's up to you. So y to the 7th divided by y to the 5th should be y to the, it's a funny way to say it, but anyway, y squared. Y to the what? 2, right? Or y to, oops. I think it's my stylus case kind of broke. I think it's because it's loose. This one you kind of have a choice. If you just use the rule, it would be 5 minus 7, which is perfectly fine. Okay. As far as I'm concerned, negative or positive exponent, one's just as good as the other. If you don't like negative exponents, you could write it as 1 over y squared. Now, the textbook, as with many authors and settings, probably goes toward the positive exponent when there's a choice. So if you look up the answers or something, that's the way they would present it, usually. Yeah, for me, that's what I don't care. Positive, negative exponents, up or on top or underneath, that's up to you. I would expect you to simplify this to one or the other, right? So you shouldn't have 2 sets of factors of y, you should end up with 1 set. Another basic rule is if you take a power of a power, then you multiply. So if I had 3 squared, so I have 2 factors, and now I'm going to list those 3 times, so I should have 6 factors of 3. Right? And then you can apply these rules together, so you can take something like, oh, whoops, yeah, getting ahead. You can't use them together until I mention them, right? Okay. So powers. There's sort of a distributive law with the exponent. So a power of a set of factors instead of a single one, you can write as single powers multiplied. So you can write the power of the entire thing or separate powers of each factor. So if I had 3y squared, I could write that as 9y squared, right? So square the 3, square the y. Okay. Now, I'm going to make a big swing to the left and talk about radicals. So what are radicals? Well, in math, I guess it's not so far to the left. It's just the matter of this symbol, right? The root symbol. So if I do things square root of 4, what's that? Or if I just ask you, what are the square roots of 4? There are 2 of them, but in the radical notation, we make a distinction. So if there's a choice, that means the positive. And if we want the negative, we would put minus. Of course, there are also things like we could have other radicals, cube roots. What's the cube? Oops, catch up here. Cube root of 27. Because in that case, there isn't another choice. There's only the one possibility, and you can actually take what the cube root of minus 27 is minus 3. Right? Square root of minus 4, though, what's that? Unless we want to worry about complex numbers and imaginary numbers, there isn't any such thing. So when we talk about radicals and roots, you're going to have to worry about, well, sometimes they're not defined because we can't do square roots of negatives. But we can do cube roots of negatives. Actually, you can take, different roots. So the little symbols, you can take 10th roots, 12th roots, whatever they are. So we have this symbolism. If this is an even root, then this number x has to be what? Non-negative. If it's an odd number, you can actually put negatives in. Okay. In many settings, because of that, there'll be an understanding we're not going to use negatives. So x is non-negative for the whole setting, so I'd have to worry about, well, is the n even or odd? So you know about this notation and roots, right? You were giving me answers, so you know what it at least conceptually means. And so if you take the cube root of x, it means if you cube that, you would get what? X, right? But if I write x to the 1/3 and I cube that, what happens if you use the exponent rules? Do we get x to the 3/3? Or x, right? So because of exponent rules, oh, these two creatures must be the same thing. So the 1/n power of x is the same as the nth root. And in those cases, there would be a choice of roots. This is the positive one, as in the other notation. So in that way, you get at least 1/2, 1/10, those kinds of things, right? So if you write something like 16, oops, come here, maybe. Oops. Have to catch up my stylus there. Come on. It's being choppy. Why? I think it's this. Yeah. Try it again. What was I trying? No, I think, 16 something. Actually, you can make sense out of something like the 5/4 power now. Because you can take 16 to the 1/4 power, which is a root, and then take the 5th power of that. And what's the 1/4 power of 16? 2 to the 5th, which is 32. So you can deal with essentially any fractional exponent. Okay. It's 1/something for a root, and then the other part's just the basic power. And so actually, there's a way to make sense out of all kinds of things. I mean, what we just did would be also 16 to the power 1.25. So it makes sense for really any number. So the base, any non-negative number, and if the exponent's any number, we can compute, or at least theoretically, there's some number associated. So all the rules we know apply as long as these are essentially numbers. So we do x to the 1.86, and we multiply that by x to the 3.04. What do we get? What's the exponent? X to the 4.90, I think. Yeah. So just add them. So they're not nice whole numbers, but they're still numbers, right? When we use this in general, the x is usually stated to be non-negative, so you don't have to worry about does that get into square roots or anything. But the exponent could be negative. You can have x to the minus 5.2, that's perfectly fine. Because that would be 1/, x to the 5.2. So all those rules still apply. So the exponent rules. The other thing that can come up is we might have an expression which is not a single label, like x or y or just a 3 or something. So something maybe 2k minus j here. And then you might have an exponent for that. So a power of 2k minus j. So if you have more interesting expressions, actually I want that one to even be a little more interesting than that. There we go. So we have 2k minus j squared. We also have 2k minus j cubed and then multiplied. Now in general, what are you going to do with this? Well, one thing that you might do is multiply it all out, which would be a mess. Usually you don't want to do that unless you have to. Okay. What I've written here are all factors, right? And so the factored form is usually better than the multiplied out form, or what you would call the expanded form. If it's in expanded form, it's very hard to come up with the factors. If it's in factored form, well, there's just one basic sequence for everything that you do to multiply it out, right? So that's always possible. So the factored form would be better. But this particular set of factors, since we have the same base, we should probably simplify that and write it as 5 factors of that same base, right? So even though the label isn't one single letter or just a number, we still have the same rules, right? And for this particular type of expression, I would probably stop there and not try to find the 5th power as some big long polynomial. There might be some reason to do that in a particular problem, but I'm not going to do it unless I have to. Okay. So, exponents, recall. One thing you have to be careful is you have these 2 rules. Whoops. Yeah, I think it's, yeah, that's it. Yeah, what 2 rules? Negative exponents and what? Fractional exponents. They both, at some point in the rule of conversion, what happens? Involve reciprocals. 1 over 5 here, and up here, though, is 1 over 3 to the 5th. And this one refers to the 5th root, doesn't it? It's one place where quick mistakes that you kind of jump over on tests and homework is getting the 2 backwards at some point. So sometimes this one gets interpreted as 1 over 3 to the 5th accidentally because, oh, I have a fraction, and you go right there. So be careful. That's the most usual thing, is when you have this exponent like 1/5, is to think, oh, fractions, and then put this one, the reciprocal, which should have went with the negative instead. But sometimes I see when you have the negative, you think fractions, and then you put the fraction in the exponent. So be a little diligent. Keep those 2 separated. They get, in your mind, they get a little bit similar because it's 1 over in each case, isn't it? But it's a little different. So don't mix the 2 up. So, there, how's that for today? And we'll convene again on Friday. Oops. Get the right.